lecture we are going to discuss how to machine and what are the problems during machining of CFRPs or carbon fiber reinforced plastics reinforced polymers. Okay, so you know we have two types of CFRPs. This we learned in our previous lecture. One that are made of short carbon fibers, and these short fibers can be either vapor grown carbon fibers or they are actually spun fibers. They are long, but we have cut them into smaller pieces. The other type is laminates. So we already learned how to work with laminates and how do we make structures. We take a big mold, we place the sheet of carbon fabric in that case, and then we infuse resin, we put another sheet of the fabric, we infuse resin, and so on. So this is how you get your structures. In the case of short fiber based CFRPs, what you can do is you can use direct molding. So you make a mold of whatever shape you need and then you fill in your resin. Now here, one advantage is that this is more or less a uniform looking material. It's not, unlike laminates, there you have completely different these fabric like sheets, but here you can treat it as one material. In fact, this is also true for carbon nanotube, reinforced plastics, that you can treat them as one material, and then you have, you place the entire, or you pour the material inside a mold and then perform the curing of the resin, and that is how you get your structure. Another option, if you want to get high quality structures, you for example want to make a bone implant, and you want the implant to be exactly of the shape of the bone that person requires. In that case, you can perform something like 3D printing. So you can perform a little more advanced techniques in that case. Okay, so this is how you make your CFRP structure. But after making it, you require certain finishing operations. You also require certain joining operations, because you don't just make the structures, but you also attach them to something. For example, if I make a very massive large wind turbine blade using CFRP, then what do I need to do? Afterwards, I need to attach these blades onto the tower of your wind turbine, right? I also may have to perform the finishing operation, because when we make the mold, you know that we place a laminate, but the edges are not perfect. We know that we'll always have slightly extra edges when we especially when we are doing this layup. So in that case, we need to remove these edges. So we need to perform operations like drilling. We need to perform milling, edge milling, cutting, and also all sorts of finishing operations. Okay, so what is the problem when we do this? Our composite materials they are different from traditional materials, that we know. So it's not like metals where you already have all the standards. This is also another challenge, that this is still a relatively new field, so you don't have all these standards for your operations. So you need to optimize, and you need to also understand that you have these thread-like structures which can peel off, which may also, not each individual rope has the exact same mechanical property or the adhesion to the resin. So because of this, we'll have some challenges or some issues. Let's see what are these issues. The first and foremost problem in the case of laminates is the delamination. What is delamination? So you know that laminates are like these layer by layer structures. When the top layer peels off from your bottom layer, that is known as delamination of the structures. Okay, this is the biggest problem whenever you perform drilling or any operation. So for example, here I have shown one sheet of CFRP, and then you have a tool which is rotating, and then performing the edge milling. Now what will happen in this case? Afterwards, if you see your finished product, then if you zoom it in, then you will see at the edges you will still have these fibers hanging outside. These were the fibers which at some point got detached from the surface or got delaminated, and that is why they were then sort of flapping. Then you were not able to nicely cut them. So this is one major problem, which is very different from your any traditional manufacturing material. This is very specific to the laminates. Now the delamination is further divided into two types. One is known as the peel up delamination. So in this case, you see there is a drill bit and that is rotating. Along its twists, some material kind of gets attached to it. That is known as the peel up delamination. On the other hand, the more common delamination is what is known as the push down delamination, where when now your drill bit goes inside and then you can see that some bottom layer that got removed, that got detached from its the previous layer. And also this kind of delamination then can lead to fiber breakage. So these are the two types of delamination. If I take the top view of this second one, push down, then you will see that you were able to drill the hole, but you did have some fibers that are not removed. So some residual fibers you will always see. Why did that happen? Because these fibers were delaminated at some point. Okay, this affected zone, or let's call it damaged zone, that is often more prominent in the direction of your fibers. Perpendicular to it, you will still have some damage, but more delamination. Obviously, you can see that your fibers are like that. So when they peel off, they will peel off like this, right? So, however, some fibers sideways will also get affected, but in the direction of your fibers, you will have a more prominent effect. So the damaged area will look like this, what I have shown here. Okay. Also, the most affected layers from your delamination are your top layer and bottom layer, because these layers are only supported on one side. The other layers, they had some support on both sides, so then they are not affected that badly. Okay, now this fiber breakage, you can say this is, in this case it is tensile, but you can also have compressive damage. So the fibers can, they can go away, they can move away from each other. So you have some compressive damage, but the more common damage or delamination is due to tensile damage. Okay, fine. Now, how do we quantify it? So, as I mentioned already, there are not so many standards in the case of the composite materials, and in fact, this is a lot of work is going on in this direction right now. As in the case of metals, where you already have all kinds of standards. So, well, however, we do have something known as a delamination factor, and delamination factor, as by the name you can understand that how much material is delaminating. What is the region that is affected by delamination? It is a measure of that, and in a while we are going to talk about this in detail. But before that, few more problems which are associated with machining or drilling. You can also have tool wear. So tool wear is a problem in a lot of machining operations, right? So here what happens is, this is a very, very common problem in the case of CFRPs, because you can see that you have a very non-uniform structure. So it is common that the radius of your tool increases. So tool wear is also one common problem. There are also some issues with the finishing operation. So we'll be talking about them. What are the reasons? First of all, so as I mentioned already, your material is very non-uniform. What do I mean by non-uniform? You have two completely different materials in one material, what you call the composite material. So you have your carbon fibers that are actually, they offer a much higher mechanical strength. They are also thermally conductive. But on the other hand, what you have, your resin is not thermally conductive. It also has completely different properties. It has a different, degradation point compared to carbon fibers, which don't degrade even at very high temperature. However, so the mechanical properties are from carbon fibers, and the other properties, the binding properties, are from the resin. So you have completely different materials. Okay, that is number one. So this is also this is an anisotropic material that because when you have laminates, you have properties different perpendicular to the plane and in plane. So this is a highly anisotropic material. So this is one problem. When we talk about the non-uniformity of these composites, it is at different scales. So in bulk scale, what I was just telling you, that you have one carbon fiber sheet and then you have a resin. So that is when we are talking about the bulk. However, when we even talk about a laminate structure, then not all fiber bundles are exactly of the same size. You may also have some twisting and entanglement of the fiber. So some weak points within your fabric also, that is possible. So that is also then non-uniformity. Then you may also have, if you think of individual fibers, as I mentioned, the entire fiber diameter may not be uniform. You may have certain bulges somewhere, you may have necking somewhere. If I look inside the fiber, if I look at the microstructure of a fiber, even there not each fiber is uniform. Or even within one fiber, if you see the microstructure, you may have voids trapped somewhere. which may cause weak points, while the rest of the, or you may have turbostratic structure, but at some points you may have some graphitic regions. So even within the fiber, so you see, this is a non-uniform material that we are dealing with. So there is definitely a high possibility. It's very difficult to set uniform manufacturing parameter for all parts of your composite. Okay. Now, because we have two materials, as I already mentioned, that thermal properties of the polymer and the carbon fiber are very different. So if you have certain heat generated in the process, which is always the case whenever you're performing, high-speed operations, any kind of drilling and milling, you will have certain heat generated. Now, in the case of metals, you know what is the thermal conductivity of your metal, and you choose your coolant accordingly. Or you also choose your machining parameters of the speed of your drill. Everything you can choose accordingly. But here we have two materials, carbon fibers, which have a very high thermal conductivity. But your plastic does not have a very high thermal conductivity, and in fact it will degrade. It in fact has very low thermal conductivity, and it may get degrade at a certain temperature, or the temperature will go above its glass transition temperature. In that case, it will start to deform. So this is one problem. What else can you think of? Yeah, the content of carbon fibers in various composites may also vary. So the most common content is 60% of carbon fibers in a CFRP. But this may also vary slightly, and depending upon that, also depending upon short fiber based composites or laminate based composites, you may not be able to use the exact same parameters in all cases for all composites. So these are some of the common problems. Now let's see how do we quantify these properties.
Okay, so how do we calculate the delamination factor? So this, I have drawn a couple of circles here. This image you can actually relate to what you've seen in the slides. So the smaller circle here, the inner circle, that is the circle, that is the size of the hole that you would like to drill. So the area of this hole is A nominal, or this circle, and then the diameter of this circle, the smaller one, is D nominal. Okay, now you see that there is some damage here. This is your damaged or delaminated area. Why is it like this? Because your fibers are in this direction. Okay, so these are your fibers. In the direction of fibers, you're going to have larger regions of delamination, and that is why this area, this entire area, what I will call this area AD. Okay, and now I draw one larger circle where I take the maximum delamination. So now this larger circle, which I have shown with red color, the diameter of this large circle is what I call D max. Okay, I'm not saying this is delamination, diameter of the delaminated region, because the area is taken only for the actual delaminated region, not for the entire bigger circle, but the diameter is taken for the big circle. Okay, so now I have some of these parameters, and now what I can calculate is the delamination factor. Now what is interesting is there is still a lot of work going on in this direction, because as I already mentioned that unlike traditional materials, you don't really have all the set parameters for composite material manufacturing. That is why we do calculate this delamination factor in many different ways. However, in any case, one of these factors should be used when you're doing your manufacturing, okay, or when you're drilling a hole. Okay, now first of all, how do we calculate the radius of delamination? This is very easy. This is where you will take the larger circle and the smaller circle, and here you can also actually calculate delamination diameter, but you'll rather calculate the half of it, so delamination radius, so R max minus R nominal. Okay, now the delamination factor, as I mentioned, can be calculated in many ways. Okay, first of all, we just calculate it based on the diameters. In that case, you have this maximum diameter divided by nominal diameter. Nominal diameter again is the diameter of the hole that you actually wanted to drill. Okay, you can also calculate this based on the area. Here you will take the AD, area of the region that is actually delaminated, divided by the nominal area, and in most cases this is the one that gives you very accurate values, because here you're not calculating, as I said, the bigger circle. It might be so that only one strand or one yarn of the fiber that damaged for a very for a large distance, but the other fibers did not damage at all. So diameter may not give you the best values or the idea of what is happening, but area may give you the exact values. But at the same time, it's more difficult to calculate the area compared to the diameter. Okay, now you can also, again, even within the area-based delamination factor, you have two ways. You can also calculate it using this second type of formula where you are sort of normalizing it. Okay, so another third way that has been proposed, and in a couple of publications you can find it, that is using both area as well as the diameter. So I have written it down here. FDA equals FD plus this entire value. Okay, so this is how you calculate your delamination factor. This is an adjusted delamination factor. Also, you can give different names. For example, the second one, the area based, you can call it 2D delamination factor because you're calculating the area and not just the direction. But this one, the first one, the delamination based on diameter, this is the most conventional one. So you have these three ways of calculating. However, you can already see that just if somebody gives you the value of the delamination factor, from that you may not be able to actually calculate the actual damage. Sometimes also completely different looking areas may have the same delamination factor, or in that, as I said, that even if you have one long strand that is delaminated, then the diameter based delamination factor can give you different values for different kind of delamination. So for example, if there is some structure where the delamination is like this, and then in some cases the delamination, although the maximum value remains the same, the delamination can actually be of a very severe nature. So if I calculate the diameter based delamination factor, because I'm just calculating the area of the maximum of the bigger circle, then it will still give me the same value. Similar things can also happen to area based delamination factor. Let's say this is my hole that I wanted to drill, but also in some cases this delamination may be very, the shapes may be very strange, and also the region where the delamination took place, that may be different, but still you may get the same delamination factor. However, these are some of the fundamental ways of some fundamental manufacturing parameters for composite drilling. Okay.
Now we talk about the potential solutions or the advancements in the techniques that that can be used now. For, say, instead of traditional manufacturing techniques, how can we modify them to get what is suitable for our composite material? So number one, laser machining. This is very commonly used for carbon fiber or CFRP manufacturing, because that we use industrial lasers for cutting, for example, PMMA sheets. So we use CO2 laser, the IR laser for cutting plastic sheets. Similar lasers can also be used for cutting CFRPs. You can make holes using lasers. You can have you can do edge milling and all kinds of operations. So that is one very common technique which is used for machining CFRPs. What are the advantages? This is industry nowadays. Laser machining is very commonly available technique. This is also relatively residual free, and it is a relatively fast operation. So these are some of the advantages. However, you also have the disadvantage of getting this heat affected zones. So when you are cutting something with laser, you are melting the material. You are actually generating heat. And again, I told you that your the thermal properties of your plastic and carbon fibers are very, very different. So it is difficult to optimize the laser parameter to cut the entire structure uniformly. And you may have, if you go to certain laser parameters that are required for removing the carbon fiber, that might be too harsh for the polymer, for the resin, and you may end up degrading some of it. So you will have what is known as a heat affected zone. That is a common problem with laser machining of CFRPs. Okay, what else can we do? You can use common drills, our standard drill bits, and we perform the same operation. However, what we have is a water jet that is associated with it. What does a water jet do? Number one, it performs cooling, and number two, it also removes all the debris, so all the chips that are being produced, and it does apply certain force, so your cutting is relatively uniform. So certain pressure is also applied by the water jet. So what are the advantages? What can you think of? Well, you have reduced mechanical as well as thermal stresses because of the jet of the water. You also have less, it's not just for the workpiece. This is also then for cooling down the tool. Your tool is typically a metal tool. So a water jet, that really helps in the case of, resharpening of the tool and to prevent the tool wear. This is very helpful. And you also have high flexibility. You using a water jet, so you have, you can use it in any direction, you can use it in any way, and your tool does not damage that much compared to other techniques. Disadvantages, well, the water needs to be microfiltered. So it should be very clean water, because if your water has any kind of particles, that can actually damage your operation, or that can then act as an abrasive, which you don't want, unless you want it. If you want abrasive, then you have well controlled abrasive where you also control the particle size and so on. But in this particular case, if you're using water jet, then you need to perform microfiltration of water. That can be relatively expensive and sort of unnecessary. What else? You know that your water will carry now all the chips that were generated, but these chips, then this water which contains all the chips, the disposal of that water and the post treatment of that water is also expensive. So these are the things that maybe you can use rather at lab scale, but when we are talking about industrial scale manufacturing, then the cost becomes very important. So in that case, water jet has some problem, or the post treatment of that water becomes an issue. Okay. What else do we do? We can also use carbon dioxide blasting, or it is commonly known as dry ice blasting. So this is basically solidified. Dry ice is solidified carbon dioxide, and now we have a jet of this dry ice during our process. Okay, so this is often mixed with air, and you have a very high pressure jet of dry ice that is blasted onto the surface, which will perform cooling, which will also perform the cleaning of the surface, very similar to what we did in the case of water. So during drilling, you can also have this dry ice jet. Okay, what are the advantages? Dry ice, always there is an advantage that your carbon dioxide is going to completely sublimate. So it's going to disappear. You're not going to have any residual on top of your surface. In the case of water jet, after you finish your operation, you also have to dry your material. So there's also the dry your workpiece. So a little bit of course, residual water is going to stay there, but that is not the case with carbon dioxide. So you get a clean surface. You don't need to worry about it very much. So that is, of course, a residue-free process. But there are also disadvantages. Now, you cannot really do machining with carbon dioxide particles. You can, they have very low hardness, and also they sublimate reasonably fast. So they cannot work as abrasives. Why are we talking about abrasives, by the way? We already have a drilling tool, so why are we talking about abrasive? Abrasive is always giving you a good finish. So for polishing operations, you will often perform, like filing, or you in the case of larger structures, instead of filing, you will have an abrasive. You rub it with an abrasive. So this is why we need, for a good finish, abrasives are always helpful. And in fact, we'll now learn how can we use abrasives in this case. Okay. Often what is used is a combination of water and CO2 jet. So this is a good balance. This is also, in some cases people have used it, and this is useful, and it seems that it yields better shapes of your structures. Okay. So now other techniques, what else? So these are some of the new techniques which I have just picked up from some of the papers. I'm not sure if they are already being used at industrial scale, but definitely these techniques have been proven to work, Okay, so you can have these flexible super abrasive belts. So if you have a belt which contains abrasive particles on top of that you can use with this is probably used at industrial scale. At least a few companies are using it. So they have these completely automated systems. So they attach these belts, or they provide these belts to the robots. So basically you have these completely automated abrasion using abrasive or super abrasive belts. How do they make these super abrasive belts? Well, one option is to coat these belts with diamond particles, and these are chemical vapor deposition grown CVD grown diamonds. Okay. Other particle, super abrasive particle, is also silicon carbide. So silicon carbide and diamond are two of the hardest materials, and industrially they are used for often for making all sorts of abrasives and tools, or the tips of the tools, or often the tools have a coating of these kind of CVD diamond or silicon carbide that prevents the tool wear. And also it provides a better finish to your workpiece. Okay, so when we talk about CVD of carbon nanomaterials, then we will also discuss how can we prepare diamonds using CVD. Okay. Yeah, another thing is that you can use ceramic tools. Ceramic tools, alumina, for example, they are also well known, and they have a low thermal wear. So tool wear is less in the case of ceramics, and they don't lose their sharpening, their sharpness. Okay, so you can use ceramic tools. So these are some of the other techniques which here and there are also probably used in industry, but definitely at lab scale they are used. Okay. What other things can you do for advanced finishing? These are some of the names that I have mentioned here: edge routing, drill grinding, and often you will use abrasives in all these cases. And abrasives can be ceramic particles such as alumina, silicon carbide, or you can have the CVD diamond. So for further reading, there are a lot of books again on machining of composite materials, or just preparation or manufacturing with carbon materials. There is one publication that I have mentioned here. I have taken some of this information from this paper, so you can also read that.